right here, you won't be asked to solve an entire truss that way, right? So you won't actually have to take an inverse or anything like that, or do the actual matrix math. I'm not going to ask you to do that for this exam. But you should understand how to manipulate the matrices, right? You should understand what dimensions to expect for a given truss and things like that. So you should understand how that process works.
Like,
Yeah.
able to set one up, maybe?
Potentially, yeah. Yeah, potentially be prepared to do that. And since you're not going to be asked to solve it, I would say the size, there's not really a limit on the size for the matrices that you might encounter, or matrix related questions that you might encounter on this exam. Yeah. On future exams, when you are going to be actually solving matrix problems, my promise is that you won't have to invert anything larger than a 2 by 2, right? And going along with that, all matrix math will be doable by hand. You can use your calculator when we get to that point, but yeah, it should all be doable by hand. Any other questions or requests on specific topics to focus on later in class today? Okay.
This is going to be posted?
It has been posted, yeah. So this is on D2L. There's a new folder called Exam Info. You can find this file in here, and then also, and I'll point these out now, we may or may not talk about them later today, but I want to at least point them out to you so you can review them. In that same Exam Info folder, I posted a document that kind of goes a little bit more in depth into a discussion on load path, specifically with gravity systems and different floor systems. So it just kind of breaks down, looking at a floor plan and identifying the joists versus the girders, identifying the direction of the floor span, looking at, the tributary areas for different elements and what the load distribution would look like on certain beams. So there's just a bunch of notes and comments in there related to this stuff that might be helpful for you in studying this topic. And then the other one I wanted to point out, and this certainly isn't the only example that will be helpful for the exam, but in the examples and practice problems folder on D2L, there's a bunch of stuff. There's a bunch of stuff related to the topics that we've covered so far. And this one in particular I wanted to point out, because this is a good practice problem related to trusses and specifically using method of observation or method of sections and observation, right? So identifying those special types of joints and things like that. Because, method of joints is, we all know how to do that. It's pretty systematic, right? You just go joint by joint, apply the equilibrium equations. So that one's doesn't require a whole lot of thinking, right? The method of joints doesn't require too much thinking. But method of sections and observation, that requires more thought. You have to be strategic in your approach. So I think this would be a really good practice problem for everybody to tackle. And so you can see that on D2L, it's going to be looking like this, right? So the first page will be the problem with a blank page in case you'd like to give it a shot before you look at the solution, and then the second page has the solution with some comments on it, okay? All right, so we'll talk about visual analysis now, and I'm going to switch. I have the PowerPoint presentation queued, but this is the visual analysis guideline that is provided to you on D2L. Instead of it within the lectures folder, I have a special folder just for visual analysis because we're going to be adding some more stuff to that. Actually, I think I already made a few extra files available to you, ones with examples on there. So this first one is the visual analysis guideline, and this was just going to be, the required reading for this lecture. And this will be a good tool or a good resource for you as you go through and work through visual analysis problems and get used to working with that software. So that's got maybe, 4 pages or so in that document. And then The other file, one of the other files is gonna look like this, where it consists of a bunch of different example views of displays, specifically focusing on a truss with a bunch of comments on it. So the stuff that you read in here, I'm gonna talk about in the PowerPoint presentation, and then next week we'll have some time, we'll probably have some time to do a demo, so I'll bring my computer in and I'll show you visual analysis on the computer and stuff like that. But this file goes through truss display things, and then the third file goes through beam stuff. So those files with the truss and beam examples, that will be helpful for you on homework 5 and homework 6. So homework 5 is going to be focused on truss. You're going to do the finite element analysis, hand solution, right? And then you're also going to model that truss and visual analysis. So that's all part of homework 5. And then homework 6 will be focused on beam finite element analysis. And there'll also be a little bit of the single axis axial force system in there in homework 6. But as far as the modeling is concerned, it'll be just beams for visual analysis. All right, so that's what's coming up. And if you have this document handy, you may or may not want to try and, just kind of follow along with the PowerPoint presentation. This will, I also posted the slides printed to PDF, so that would probably actually be better if you have that on hand to follow along. So go ahead and do that. Let's see. There we go. Visual analysis. Oh, and by the way, I keep meaning to ask this question and then I keep forgetting, but the bridge in this image that I've been using for my intro slides, who recognizes that bridge? All right, you're the one that wrote about it in the homework 1? Okay, I thought so. I knew someone wrote about it. So yeah, this is the bridge over the New River Gorge in West Virginia, and it's really cool. And forgive me if I'm remembering the details wrong, but I think it was the third largest arch bridge or something. So a pretty cool structure there. Very scenic. All right. So going on, visual analysis. This is a free software for the educational version for students, all right? So this is just a screenshot of the visual analysis website, and you can go to that website, submit your email address, and request a free license to install on your own PC if you would like to do that. Visual analysis is also installed on all of the computers in the Tate Lab. So if you don't want to deal with it on your own computer, or if you don't have a compatible machine, then use the computers in the Tate Lab for your work in this class. I did check, and they should be all updated to the latest version of visual analysis, so the license should be good through next September. But if you run into any issues, just let me know with the computers in the Tate Lab, and I'll contact IT on behalf of all of us. But I did check the other week, and we should be all good to go. If you want to use it on your own computer, I highly recommend that you submit the request as soon as possible. Sometimes it takes them a little while to just get it together and approve it. So, I recommend you do that soon. It does require Windows 8 or 10 and higher, so just keep that in mind. It's not compatible on Mac machines. So, all right, so when you open visual analysis, this is what you will see. The user interface is pretty friendly once you get the hang of it, the layout and everything. So that's what I'm going to break down for us today. So first up, at the top left, you'll see these main tabs, right? So you've got the home, structure, loading, and tools. Then you've got the view tabs, right? So we're going to work with different views in this class, mainly model view and results view. We're not going to do anything with design view in this class. So just skip that tab altogether, all right? I think most of the design features are not active in the student version anyway, so so we're just not gonna deal with it. And then the one on the far right, the report view, we'll talk about that later in the semester. So initially, we're just gonna be focusing on the model view and the results view. And then there's another one that'll pop up once you have a model, which we'll see later. But over on the left side, we have the project manager panel. And this is where you're going to be doing a lot of inputs and manipulation to, see what you want to display, and you can use that project manager to change some values if you want to. So we'll look at all of that as well. And you'll notice that the tab options within the project manager, we got modify, model filter, etc. Those will change based on what view you have selected in the view panel. So when we've got model view selected, that's what you're going to see in the project manager. We'll see later what it looks like when we have result view. So one thing I'd like to emphasize a lot is for this class, we are only going to be modeling two-dimensional systems, right? So you absolutely can model 3 dimensions in visual analysis, but we're not going to do that in this class. This, is a little bit more advanced. So when we model two-dimensional structures, we want to make our lives a lot easier and always select plane frame in the structure type options. The default will be space frame. That's what you want if you're going to model 3 dimensions, right? You can use space frame to model 2 dimensions, but you have to do a lot more stuff to make it work. So just simplify your life, select plane frame as the very first thing that you do when you open visual analysis. So now I'm going to just show you a little bit of the differences between space frame, plane frame, and why we do that. So if we were to model a single bay, single story frame in a space frame in 3 dimensions, every node would have 6 degrees of freedom. All right, so that's 3 translation and 3 rotation. So the node that I've circled there, that represents what we would call a free node in visual analysis. And that's because there are no external restraints applied to that node, right? So it connects 2 beams and a column, and there's also an area element that is defined in between all the beams. So it's an important node. It's connected to the structure, all right, but it is free to move and rotate with that structure, all right? So there's nothing restraining it. At the base of the structure, that's where we would want to define supports. So if we had a pinned support, that is what you see on the far left, all right? So you have all 3 directions restrained from motion. And then if we want to model a fixed support, we would have to add the 3 rotational restraints. So that's your Rx, Ry, Rz. So the fixed support would have all 6 degrees of freedom restrained from motion. Now, if we were just interested in a 2-dimensional frame, right, then we have 3 degrees of freedom. So a lot less stuff to check, right? A lot less boxes to check, a lot less things to think about. So your free node would have 3 degrees of freedom unrestrained. A pinned support would have 2 restraints applied, right? Dx and dy. And then in order to model a fixed support, you would have to add the Rz restraint. In this class, you're going to get experience modeling beams, trusses, and frames. So these are all things that I'll introduce in this presentation, and then as they come up in class, we'll talk more about them a little bit, well, depending on what it is, right? You've already got the material, most of the material for trusses and beams, and then frames we'll deal with later in the semester. So that's the one where really, we'll talk about frames more later. This initial discussion on visual analysis will focus more on beams and trusses. So looking at that truss, right, so you can already identify the supports, right? The supports are shown in gray arrows, applied loads are shown with green arrows. And it's pretty obvious what's going on with the beam and the frame, right? but what the heck is happening with that truss? Why are there rotational supports at every node? So that's something that's unique to trusses that we will talk about later once we get through the rest of this introduction to BA stuff. So a couple of modeling considerations that we need to think about for any structure that we model. Focusing on the structure, and then we'll also look at a couple considerations related to loads. So first, with regard to the structure, right, you've got node placement. That's kind of the first thing that you're going to define is where your nodes are going to be. That's going to define the length of members between those nodes, etc. And then node restraints are also very important because that's going to turn your structure from something that's unstable to something that is stable. Those are your options for two-dimensional modeling, right? We already talked about those restraints. And the member connectivity, that's another big one. So as you know, right, members can be connected with rigid connections or pinned connections. The pinned connections between members, we also can call that an internal hinge. We know moment is equal to 0 at that location. So we're going to talk about how to model that in visual analysis and specify whether you have a pinned connection or a rigid connection. And then member properties are also an important thing to remember. So that involves the material that you're modeling and the specific cross-section or geometric shape. With regard to loads, right, you want to think about the application. Is it a point load or a distributed load? We'll show you how to define each. And then the type of load, right? So we've talked about the different types of loads, but we haven't really gone into detail yet. But you are aware that there are dead loads, live loads, and different environmental loads, right? We looked at that a while back, very briefly, but we touched on it, just defining what they are and a few differences between some of them. So for now, we're just going to worry about adding loads to the structure, and we'll just assign them all to the dead load case. One thing to remember with that dead load case is in visual analysis, it's going to automatically include the self-weight of the member. And that's a good thing for when you're actually modeling something, because then you don't have to worry about calculating the self-weight and adding it. But for this class, you're going to disable the self-weight in the dead load case for all scenarios, right? And because the reason for that is because we want to really compare our hand calculations and results to what visual analysis is telling us. And if you're disregarding self-weight in your hand calculations, then we want to disregard self-weight in the visual analysis so that we can make that direct comparison. So in this class, always disable self-weight. Load combinations then, so once we get into defining all the different loads, we'll talk about, at the end of the semester, we'll revisit this and talk about how to combine dead, live, wind, and things like that. But again, for now, just worry about assigning the loads as they're applied and treat them all as dead loads with the self-weight disabled. All right, so now we'll focus on some of these modeling considerations. So first up, all right, we got in the project manager, when you're in model view, right, you want to go to the modify tab. And you'll see that the options that show up in that tab will update depending on what is selected within the view panel. So right now nothing is selected, but if you select a node, right, so this node is selected in this example, now the specific details for that node have shown up in that project manager, right? When you select a node, you can then use that project manager to change the name of the node if you'd like, change the coordinates, or assign node restraints. If you select a member, right, it'll update with information that's relevant to that member. And again, you can use that panel to change the name, assign a shape or material, or assign end connectivity. So speaking to that end connectivity, this is where you would define whether it is a rigid joint or a pinned joint. So This is specifically related to connections to other members, so it doesn't really make a difference if that joint connects to a support or not. So just worry about connections to other members. A rigid joint, right, that is going to be the default setting for all members when you draw them. So all members will have that rigid connect type defined. If you want to change that, if you have a pin connection between members, then you want to change that to simple connect on the member. The other options that show in the drop-down menu would be representing one end of the member has a rigid connection and the other end has a pin connection. In this class, you won't have to worry about that. We're just going to be doing all rigid or all simple connections. The rigid connect, right, if we do a deep dive into what this looks like, you can see under the releases, right, this is still with that one member selected. Releases, it will show all these different options, and there are no end releases, right? So with the box unchecked, it's saying it's rigid in all of these regards. If a pin or simple connect option is chosen, then effectively what you're doing is you are releasing all the abilities of moment transfer, right? So you're letting go of moment, and so checking these boxes says, okay, it's released in both directions for moment. So that is another way that you could actually go and define your member connectivity is through this release panel. It's a little bit more involved, right? But you can get very specific as to what's released and what's not. You can get more specific than changing the type. But again, in this class, that's beyond the scope. We're only going to be dealing with purely rigid or purely simple connections. But that's what that means. So, all right. So now looking ahead at frames. All right. As you know, there are two different types of moment resisting frames that we defined so far in this class. One has pin connections at the base of the columns, but rigid connections between the beam and column. And the other has fixed supports at the base, but pin connections between the columns. Both are stable configurations, right? Remember that from lecture 2 or 3. But they're going to behave a little bit differently. Remember the deflected shapes. So modeling them, right, would look something like this, where for the option over here with the rigid joints, right, you would just leave all members with their default settings with regard to connectivity and have the pin supports at the base, whereas for the other option where you have the columns pinned to the beams and fixed at the base, right, you of course have the fixed support with a moment restraint applied, and then you would have the pin or simple connect setting on the beam, right? You don't need it on the column, but just on the beam because that takes care of it. And so those green circles, that represents the moment release. And that won't automatically show up. That's a setting that you have to select in the display options to view the member releases. But it's a way that you can check to see, okay, do I have moment releases on the members that I want moment releases on, etc. Now with trusses, so this is where we get into why trusses have all those moment restraints. With trusses, right, we have pin connections between all members. So in order to model that appropriately in visual analysis, we need to apply the simple connect setting to every single member in the truss, right? So every member should have those green circles show up if you turn on that view display setting. But the problem is, if every single member has moments released at their ends, then the node within that model can technically spin in place, right? So it's going to move, it's going to displace with the truss, but because all the moments are released around it, it can spin in place, And so that's going to tell the model that this is unstable and we can't analyze it. So in order to get around that, you have to apply moment restraints at every node. So that's going to prevent the node from spinning in place. But it's not going to actually allow that structure to transfer moment, right? So it's not a real moment restraint, but it's just a way to kind of, inform the model of how to treat it, right? All right, so now with beams. Since beams in this class, we've looked at beams that have internal hinges, right? But with regards to visual analysis, I'm not going to ask you to model that scenario. So all the beams that you will be modeling in this class will be continuous, no internal hinges. So that's nice because then you can just leave it with the default rigid connect setting, right? So that translates to a continuous behavior. One thing that is a fun, I say that sarcastically, a fun thing to deal with visual analysis is that there are often display issues. So you may want to view the results, something like this, where it shows you what the reaction forces are, right? So that's the output. You input the applied loads, right? And you input where the supports are and what type of support it is. And then the output will be the magnitude of those reactions. But sometimes they don't display very nicely. Sometimes that can be fixed by zooming in or out of the view, but other times it's just, it doesn't work out very well. So in that scenario, if the result or if any result that you want to or are asked to display doesn't show up properly, just feel free to go ahead and clarify it in your submission, right? You can write it in by hand or you can, add it in with text like that, whatever works best. All right, so a few different types of views that you'll be dealing with in this class. And remember, I said we're not going to do anything with design view. So these are all different view panel options within visual analysis. Model views will be used to show the general configuration of the beam or structure, including lengths of members, the shape of the member that you selected, right? So the W8 by 10 showing up, the applied loads, magnitude and direction, and what supports are defined. Results views will be used to show the relevant results that we want to see. So you'll notice here we have the reaction forces displayed, and in the background you can see the undisplaced position of the beam with the applied load that's causing this deflected shape, right? So that's going to be something that you'll be asked to do as well. You'll also notice that this information is not showing up in the results view. So you're going to have to manipulate some view settings in order to get rid of any extra information that you don't want to show. And then there's also a member graph, which is a view option that doesn't exist until you have a model defined, so we didn't see it in the first slide. But the member graph is, for a beam, the relevant values would be the elastic curve, which is dy, right? So that's just the deflected shape, the shear and moment diagrams. Now, if you're modeling a beam, visual analysis should automatically understand that these are the three graphs that you're interested in, right? But in the case that it doesn't, you can go in and specifically request it. So I'll demonstrate that when we get to next week, when we get to show you visual analysis in class. But the directions are listed up there, right? So all the information you need is contained in this slide and in this presentation, and also in the visual analysis guideline, and then in the additional files specific to trusses and beams. So, all right. With frames, all right, here's just a few examples of model views and results views for frames. again, we'll deal with frames later in the semester. But one thing that I do want to point out that's different with frames compared to the beam results view that we just looked at, or for the member graph anyway. For frames, instead of showing the deflected shape, the dy curve, we're interested in the axial force diagram, right? Because a frame it should be able to resist axial force, shear, and moment. So we want to see those three graphs for a frame member versus for a beam. We don't care about the axial force diagram because there's not going to be axial force in just a beam, right? If you have a beam column, then yeah, sure. But just beams with transverse loads and moments, no axial forces. So the other difference between beams and frames with this specific member graph is for a beam, you'll be asked to show the entire beam in one graph. So you're going to be selecting all the elements of the beam to display on this graph. For a frame or for a truss, you're just going to be selecting one element at a time, right, to show those. All right, now with trusses, we have a few different types of displays again. So the model view is shown here with, again, applied load, all the restraints that are applied. So even the ones that aren't true supports should show up on the truss, right? It's understood in the context of this class what that represents. And then your results views, usually you'll be asked to show something like this. So one that shows the displaced shape and the reaction forces, with the undisplaced shape showing the applied loads that cause it. And then another results view that you'll be asked to show is one like that shows the internal axial force of each member. So again, I'll show you how to do that, but it also should also show up in this presentation later on. Now with the member graphs on a truss, it should look something like this, where you have only axial force in every single member, right? So shear and moment should be 0 for a properly modeled truss. All right, so now going in, let's see. Actually, you know what? I think this is a good stopping point. So we will pick up and get more detailed on truss modeling and visual analysis stuff next week, because I'd like to spend the remaining 15 minutes going over some exam stuff, right? But any questions so far? Okay. All right.